Welcome to our lecture series on protection technology. These 3 Siemens Power Academy lectures are designed for those who want to expand their knowledge and understanding of relay protection for distribution and transmission grids. Today, we will focus on distance protection in distribution grids and distance protection for short lines and cables, which is mainly for professionals from distribution grids. We will record the webinar and make the recording and the slides available to all participants. Please type your questions in the Q&A field. We will answer these during the dedicated Q&A session after this series. And now, let me hand over to our expert, Siegfried Lemmer. The stage is yours.
Hello and welcome to this session on distance protection in distribution systems and for short lines and cables. This session has a little bit a strange title. The reason is I combined 3 different topics in this session, which are independent topics, which show up pretty often in distribution systems, but they can also show up in subtransmission or some of the topics even in transmission systems. Let's start with the first topic. The first one is zone setting for short lines. What additional topics do we have to consider if we apply distance protection to short lines? Where are the limits? And to discuss this, I would like to use this simple example. That's part of a distribution system. You see a transformer from subtransmission to a 20 kV system, and then a distance relay protecting an outgoing feeder. And this feeder is in this case a cable, 1 kilometer long only. That is where the short cable comes in. And you see here the ohms per kilometer for the resistance and for the reactance, 0.12 something. They are both in the same range. And that shows us already a bit a difference between overhead lines and cables, and also depending on the voltage level, you have a different line angle here. You see the resistance and the reactance have nearly the same quantity, and that means the line angle in this case is around 45 degrees, not as the 80 or 85 degrees we, for instance, find in overhead lines in transmission systems. Now let's talk about the setting of this distance relay. What are the setting rules for zone 1? For zone 1, we normally set the reactive reach to 80 or 85%. So let's assume we want to set it to 80%. The total reactance of the line is 128 ohms. And if we set it to 80%, our setting is roughly 0.1 ohm. What about the R setting? The R setting depends on the fault resistance we want to cover. And let us assume somebody calculated the fault resistances and the setting which results from that. And let us assume the result was 1 ohm. Then we need a setting for the first zone, which has an X value of 0.1 ohm and an R value of 1 ohm. What you see in this context is that these 2 settings they have a complete different background. The X setting depends on the length of the line, and the R setting depends on the fault resistance we want to catch, which has nothing to do with the length of the line. The good thing is with quadrilateral setting, with quadrilateral characteristic, we can set these values independently, but we will see that has some limits. If you apply a distance relay with a Moe circle, with a Moe setting, you can't do these settings independently, and that means with the short reactive reach, you have also a very limited resistive reach, which limits the application there. But let's assume we want to set these values, 0.1 ohm and 1 ohm. How does the first zone look like? That is our complex plane, resistive values to the right and reactive values upwards. I can put in here the cable impedance, so you see the 45, nearly 45 degrees. And now the upper limit of the first zone is 80% of the cable reactance. So it's a bit lower than the end point of this cable impedance. And the resistive reach is 1 ohm, so it's somewhere here. So you see we get a pretty extreme shape of the first zone. You can set it. The question is, will we have problems with that? And in this case, the ratio between the R setting and the X setting is 10. And the point here I want to discuss a bit more in detail is that this setting can lead to measurement issues or increased measurement errors, which can cause problems. So you should be aware of that. So the question is, why does this wide setting, or why can this wide setting cause problems with the measurement? To understand that, I would like to discuss the influence of the measuring angle error. Remember, our distance relay has to measure the complex impedance by measuring currents and voltages. And these currents and voltages are measured through current transformer, voltage transformer, measuring input in the relays. And on this way, of course, you can have some angle errors. If you have the same angle error in the voltage part as in the current part, if you divide voltage by current, they more or less compensate each other, but you can have a resulting angle error. And that means the measurement of our complex impedance we do to find out where the fault is subject to a certain angle measurement error. And I will illustrate that in a few drawings. And in these drawings, I assume a pretty high angle error of 5 degrees, just to make it visible in the drawings. In reality, the angle error will be smaller, but with the 5 degrees, you see what happens. Let us first of all assume we just have an overhead line, where the line characteristic has 85 degrees, 80 or 85 degrees. And now let us assume we measure this impedance, that was the impedance to the fault, we measure this impedance with an angle measurement error of 5%, then it would mean we would get this black arrow, that would be the measured impedance. And if you compare, we are interested in the reactance, reactive part of this impedance. If you compare now the difference in reactance, I indicate that here, there we see even with a 5 degree angle error, you get just 1% measurement error in the reactance measurement. So that is not a critical thing. The 5% are already pretty high. If we, for instance, assume 1 degree angle error, we get a reactance measurement error of 0.14%, which we can more or less neglect. It already looks a little bit different if we do the same exercise with a cable. We still assume we have no fault resistance. We just have a fault outside the zone on a cable. We would measure this point on the right diagram. And if we now assume again a measurement error, an angle measurement error of 5 degrees, we would measure this thing. And you see here, just because the line characteristic is 45 degrees here instead of 85 on the left side, the reactance measurement error will increase. We have the same angle measurement error in both diagrams, but the resulting reactance measurement error is much higher. And again there, if we come back, say, okay, the angle error, measurement error will be 1%, we end up at 1.7% reactance measurement error. which is still an acceptable thing. But that was the case with the cable without fault resistance. Now let's come back to our example with the extreme setting. We have here our zone, and if we now assume we have a fault just outside the zone with a maximum fault resistance we expect there, the measurement would look like this. That means we measure the impedance to the fault without fault resistance plus the fault resistance. That means the result would be there. That means the total complex impedance to the fault, piece of cable plus fault resistance, would be this one. And this complex impedance now itself has an angle of 7 degrees only. And if we now assume only 1 degree angle error, we end up here. That means if we measure this fault, which is a bit outside the zone and a fault resistance of roughly 1 ohm, if we measure that with an angle measurement error of 1 degree, we get a 14% measurement error in the reactance. And that can bring us into the zone and can give us a wrong trip. And that is the reason why this extreme setting should be avoided. And to avoid these problems, we recommend to limit this ratio, resistive setting divided by reactive setting of the first zone, limit that to a maximum of 3 for short lines and cables. That, of course, limits also the sensitivity. That means you cannot catch faults up to 1 ohm in this context. Or another alternative is to set a slope for the upper limit of the zone, which can avoid wrong trips. This shows the example. If we limit the setting to 3, then a fault at the end or a little bit outside with a certain fault resistance would end up there. If we measure this fault with an angle error of 1 degree, we would get this 6% reactance measurement error. And that is in the range where we could say, okay, it's acceptable. Important thing is, if you have faults without fault resistance, that means if you measure something which is on the line characteristic, the shape has no influence. The problem shows only up if we measure faults with a significant fault resistance which are just a bit above or a bit below the limit of the zone. And now what does the slope give us? If we set a slope here, we start the slope at the point where the zone limit crosses the line characteristic. Then you see the bigger the fault resistance is, the more we take the reach back. And that is a thing, that's one reason where you sometimes find in distance relays setting where you can give a little bit a slope into the upper limit of the zone characteristic. And with this, you can allow a wider setting. Another thing we have to take into account is the high source impedance ratio we may get with short cables. So first question is, what is a source impedance ratio? If we draw a single phase equivalent for this circuit here, transformer plus cable, we get this thing. So you see on the left side the replica for the infeed, in this case basically the transformer impedance, and then we see the impedance which represents the line, and then at the end of a line, a fault. And here, this source impedance ratio is defined as follows. It's just the ratio of the source impedance divided by the line impedance. And in our case, we can calculate the source impedance from the transformer data. You see here these 12% transformer data. And from the cable, we also had a look at the data. In this example, the source impedance ratio is roughly 20, 18.8. So what does a high source impedance ratio mean in this case? The problem here is we may have, if we have a fault at the zone limit where we have to be accurate, where we have to do an accurate measurement, we have a pretty low voltage if the source impedance ratio is high. And we can make for this case a calculation. How big is the voltage if we have a fault at the zone limit at 80%? This calculation is shown here. You see we have a driving voltage, and we can set up this circuit just in secondary values. And in secondary values, the driving voltage is 100 volt, which is the secondary voltage of our voltage transformer, divided by square root of 3. And then behind this voltage source, we have just a voltage divider. That means the voltage our relay measures is the impedance of this piece of line divided by the sum of the two impedances. And if we calculate that, we get a result in our example of 2.4 volts. And now the point is we have to measure this 2.4 volts with a certain accuracy. If you think about a normal meter, which may have an accuracy of 1%, then this 1% is always referring to the range of the meter. In our case, the range would be the range of the measuring input. It's something like 60 or 100 volt. But here, if we want to measure the impedance with an accuracy of, for instance, 5%, we also have to measure the voltage with the same accuracy, but not related to the 60 volt, which is the range of the input. We have to measure the remaining voltage, our 2.4 volt, with an accuracy of a few percent. And that becomes difficult if the voltage becomes smaller and smaller. 2.4 volt is still in a range which is acceptable. So our recommendation in this context is the measured voltage, if we have a fault at the limit of the first zone, that is where we have to be accurate, then the measurement voltage should not be less than 1 volt. And that is nearly equivalent to a source impedance ratio of 60. You see from this consideration, the source impedance ratio is the ratio of the source divided by the full line. If we calculate the voltage, we always take the 80% of the line, so it's not completely convertible. But as a rule of thumb, you could say, if you see somewhere in the system a source impedance ratio which is above 60, imagine the cable is even shorter, then you should be careful with distance protection. You should be aware that then the accuracy is limited. You may have to reduce the reach to avoid problems with overreach, or you should think about using differential protection, for instance, instead. That was the first one of our 3 topics. Now we come to the second one, applying distance protection in systems with earth fault compensation or isolated neutral. You find that sometimes in distribution systems. In some countries you also find it in subtransmission. You also find it in industrial systems. You will not find it in transmission systems like 400 kV or higher. There, nobody does earth fault compensation or isolated neutral. It doesn't make sense there, or it's not possible there. So what is the special thing in these systems? That is an example for a system with earth fault compensation. That means you have here a transformer shown on the left side, and the transformer start point is grounded via a coil. This coil is called compensation coil or Petersen coil. And the effect of this coil is that it reduces the earth current in case of a phase to ground fault. If you have in such a system a phase to ground fault, then the capacity of the healthy phases plus the transformer drive a certain capacitive current at the earth fault location. And this current is compensated, that's the blue current in the picture, and this current is compensated by the coil current, which is indicated in green, and both currents nearly compensate each other so that you more or less have no current flowing at the fault location. I will also show a separate video on these type of systems where I explain this a bit more. But just for the functionality of the distance protection, it's important to understand the current we see there is pretty low. One advantage is that if that is an arc fault, the arc fault will disappear without any protection interaction. But for the distance protection, the important thing is the current is so small that the distance principle doesn't work there. That means we cannot use in these systems the distance protection to detect these faults. We have to use other things. For instance, the sensitive directional earth fault protection to do that. So in these systems, the distance protection is only responsible for phase-to-phase faults, three-phase faults, and a few other things. There has been, years ago, there has been significant research, because theoretically you can imagine, now why should that not be possible? You can think about setting up equations using the same distance principle to try to calculate the fault distance. Theoretically it's possible, but practical experience shows that these equations you obtain there, these equations are pretty unstable, so the result was distance protection cannot be applied to catch these faults. That means we have to focus on the other fault types. One thing we have to take into account is that at fault inception we have some transients, so there are a few transients going on in the beginning of such a fault, and these transients can lead to a pickup of a distance protection, and that has to be avoided because the distance measurement doesn't work in these cases. That means normally a distance relay which is applied in such a network will have a certain timer to suppress these transients at the very beginning. But we have to consider one thing. If we have a single phase to ground fault, we can continue operation of the system. That is one of the advantages. The biggest advantage is that many earth faults stop without any interaction. Sometimes it's not possible. Then we can continue operation. We should not continue it for days, but at least we can continue operation for minutes. But in this situation where you have a permanent earth fault and you continue operation, you have to consider that you have a special status in the system, and we should look at that. The point there is, normally, if the system has no fault, you have a balanced system. You see here in green the phase to ground voltages of the three phases. They are symmetrical to Earth. That means in a 20 kV system, the phase to ground voltages of all three phases are 20 kV divided by square root of 3. And between the phases, you have the 20 kV. If you now have an earth fault, a permanent earth fault, and you continue operation with a permanent earth fault, then the shape of this triangle remains the same because we have no big currents flowing, so no short circuit things happen. The only change is that one corner of this triangle is connected to Earth. Before, the center of the triangle was the earthing point, and now one corner, that's the corner of the affected phase, is connected to Earth. And that means the two other phase to ground voltages increase. The phase to ground voltage of the affected phase is 0. That's why we don't see it in this picture. And the two other phase to ground voltages increase by square root of 3. That means in a 20 kV system, we have suddenly a phase to ground voltage of 20 kV in the two other phases. And that increases, of course, the risk if we have weak points somewhere in the insulation and we suddenly increase the voltage by square root of 3, then we have a certain risk that we get another earth fault, a second earth fault, on a different phase at a different location. And the interesting point is that it is at a different location. And that is a thing which normally will not happen if you have a system with grounded star points, that you have two earth faults at two different locations at the same time, because that is independent. That happens exactly at the same time is pretty rare. But here the point is, as we increase the voltage in the whole network, and as we may continue the operation of the system under earth fault condition, we can have longer time span where these increased voltages are there, and then we can have a risk that we have a second phase affected. And then the result is we have a double earth fault, and we call it cross-country fault because it can be at two different locations in the network, and that is a short circuit. And that is a point where the distance protection has to do something because we have short circuit currents flowing. And that means if you apply a distance relay in such a system with earth fault compensation or isolated neutral, you need a special treatment for these double earth faults or cross-country faults. Why do we need a special treatment? We need a special treatment because if we have such a situation, this means that two lines or two cables in the systems are affected. So one fault is on one line, the other fault can be on a complete different line, and it is sufficient to disconnect one line only, because then we take out the second earth fault, and then we bring back the system in a state with one earth fault only, and there we can continue operation. And having that in mind, we have to distinguish two different cases. Let's start with the left one. We have a double earth fault situation, and we are talking about protection relays which see both earth faults. Because the protection relay normally has different zones. That means it does not see only faults on its own line. It also looks with the other zones, depending on the characteristic, a bit wider into the system. And that means it detects, okay, we have a cross-country fault, and it also sees which phases are affected. And now, if we keep in mind, it is sufficient to disconnect one affected line only and then continue operation with just having one earth fault, then we have to agree which of the two faults should we disconnect. And that is where the so-called phase preference comes in. That means we must set up a rule for all relays which see both affected phases. That means we have a couple of relays in the system. They say, okay, we have a cross-country fault where phase 1 is affected and phase 2. And then all these relays must agree, okay, in this situation, phase 1 and phase 2 affected, we want to disconnect the line with the phase 1 to ground fault. And for that, we have a rule, and that is called the phase preference. And there are different concepts for that. You cannot say one is better than the other one. The important point here is all relays must have the same rule. And then all relays know, okay, I will only trip the line. I see that I have a phase 1 and phase 2 cross-country fault, but I will only trip if the phase 1 to ground fault is on my line. All other relays, that means even the relay which sees the phase 2 to ground fault of this cross-country fault on its own line, would in this case not trip. It would wait for the other one to trip. Then the system goes back into a state where we have only a single earth fault and where we can continue operation. Depending on the structure of the system, you may sometimes have the situation that the relay sees only one of the two faults, depending on the setting. And then, of course, it cannot make this phase preference story because it doesn't know which other phase is affected. And the pattern there is it sees a pickup in one phase. It sees an earth fault. That is a pattern which also happens at the beginning of a fault due to the transients. But if this state remains there for a time, then it can say, okay, it looks like a cross-country fault, but I see only one of the two faults. And then the only thing you can do is you can trip this thing after a certain delay. So that was applying distance protection in a system with compensated network, with earth fault compensation, or with isolated neutral. The last thing I would like to discuss is the application of distance relay on mixed line. That means where we have line which consists of an overhead line part and a cable part. That is also a thing which occurs more often in distribution systems, but you can also have it in subtransmission or even in transmission. We are here in the region currently talking about a project where we upgrade a 220 kV line to 400 kV line in a densely populated area where parts of the 400 kV line have to be put underground. That means there we have even a 400 kV line which has, in this case, even two cable sections in between. So what is special there if we have this type of application? I take here a simple example. I assume we have a line, whatever voltage it is, distribution or subtransmission or even transmission. In this case, we assume 6 kilometer overhead line. Then we have a connection point, and then we have 2 kilometer cable. And I will discuss two topics there. The one topic is the setting of zone 1 and also of the other zones. There we have to look a little bit how do we calculate the impedances, and we also have to look at the residual compensation factors, because setting of the residual compensation factors in this case is a little bit a tricky thing. And another thing we have to look at is what are we going to do with auto-reclose. So if we have overhead systems, we normally do auto-reclose, but if we have such a mixed system and we have a cable fault, doing auto-reclose on a cable fault is not a good idea. That means If we have active outer reclose function, we should block the outer reclose if the fault is in the cable part. And there are two options to do that. One is using the fault locator, that is the cheaper one, and the other one is installing a separate differential protection that is a concept where you need much more effort. So let's first of all look at the zone setting. If we have this system, of course we need the line data for the overhead line and for the cable. I've shown here the data we need. That means we need the positive sequence, resistance per kilometer and reactance per kilometer. And we also need the zero sequence quantities, resistance per kilometer and reactance per kilometer for both the overhead line and for the cable. So if we want to set now the distance relay first zone to 80% of the line, normally the 80% means we set it to 80% of the line reactance, which is for a homogeneous line equal to 80% of the line length. Here we must be a bit careful, as the reactance per kilometer is different on the overhead line on the cable. We still set it to 80% of the total line reactance, but we should have in mind that this does not mean that 80% of the total length. That means of our, in total, 8 kilometer in this case. So that means the first thing we have to do is we have to calculate the total positive impedance of the feeder, reactance and resistance. We can do it like this. We take the 6 kilometer overhead line multiplied by the reactance per kilometer of the overhead line plus 2 kilometer of cable multiplied by the reactance per kilometer of the cable. Then we get the full reactance of the whole feeder, and from this one we take 80%, and then we have the first zone. Have in mind it's not 80% of the length of the feeder. So that's the easier part. Then we need the residual compensation factors. We have to calculate the residual compensation factors, and they can be calculated from the positive sequence data and the zero sequence data. You may know the formulas we have there, but the problem is these both sections have different compensation factors. So the question is, which one should we set for the distance relay? And there the important consideration is the distance relay has to be accurate if we have a fault near the zone limit. If we have a fault at 10% of the line, we don't have to be accurate. So the compensation factor is not that important. That means we assume a fault at the zone limit, 80% of the positive sequence impedance. And for this fault location, then we calculate the residual compensation factors. That means these factors are somehow between the factor we could calculate for the cable data and for the line data. That means the first step is we have to find out where is the zone limit. It's not 80% of our 8 kilometers. It is somewhere on the cable. We can make a rough estimation. That means the first thing is we have to find out where it is so that we know which length of the cable, so this part of the cable here, has to be taken into account if we calculate the residual compensation factors. So how can we calculate where the zone limit is? We know the impedance of the first zone, that is the X of zone 1, or the reactance of the first zone. We know the reactance of the overhead line, that is reactance ohms per kilometer of the overhead line multiplied by 6 kilometer. That means if we subtract from the whole reactance of the first zone the reactance of the overhead line, then we get the positive sequence reactance of this part of the cable, which is in the circle there. And if we divide that by the ohms per kilometer of the cable, then we get the length of this cable part in the circle. And once we have the length, then we can calculate the total zero sequence impedance from the relay to this end of the first zone. It is the total zero sequence impedance of the overhead line part. That means the 6 kilometers multiplied by the ohms per kilometer of the zero sequence system, plus the length of the cable from the connection point to the end of the first zone multiplied by the ohms per kilometer of the zero sequence system of the cable. Then we know the total zero sequence reactance of this part of the system of the first zone, and then from that we can now calculate the compensation factors according to this formula. That is the calculation for the Kx, for the reactance compensation factor, and you do a similar calculation for the resistance, the Kr. So that was one thing. The second thing I would like to discuss is what are we going to do with auto-reclosing. And for faults on an overhead line, we assume we want to do auto-reclose. If we have a fault on a cable, we know auto-reclose on a cable is normally not successful. It only gives additional stress to the system, so we want to avoid it. And one approach to do that is using the fault locator. And that would be the normal application for instance, in distribution systems. And if you look into our relays, you see that we have two different versions of the fault locator. One is the normal fault locator and the other one is the fault locator plus. And what we need here basically is the fault locator plus, because this fault locator has two features which make sense in this context. One feature is it can take into account a line which consists of several sections with several parameters. And that is the case what we have here. In this case we have two sections with individual parameter. That means you can set the line data for different sections individually. And the other option we have there is we can, if possible, this requires that we have a communication link in between. We can also activate the double-ended fault locator if we have the possibility to do communication, which really increases the accuracy of the whole thing. We must have in mind the fault locator has, of course, always a certain measurement error. That means we are not able to catch exactly or to make a really 100% precise detection is the fault on the line or on the cable. That means if we have a fault near this connection point, the fault locator may give us a wrong decision. This can be reduced by using the double-ended fault locator. Then it becomes better. But theoretically, there's always a certain risk. That means we can end up in a situation where we have a fault on the overhead line just before the connection point, where we do no auto-reclose, or that we have a fault just behind the connection point on the cable and we do auto-reclose. So that risk is pretty low, but you can have that situation. You should be aware of that. If you want to avoid that, there is a second option. That option uses a separate differential protection. We assume that this connection point, there is no switchgear there. That means we have no circuit breaker there which can interrupt the current. But if we have there the possibility to install a current transformer, also to install a protection relay, I would imagine that could be the case, for instance, in a 400 kV project. Then you can, in addition to both distance relays on both sides, you can set up a current differential, line differential relay just across the cable section. It cannot trip the cable at the connection point because there is no circuit breaker, but you can then use the trip signal of this distance protection on one hand to trip the right breaker, but also to block the outer reclose for both distance relays. But as I said, that requires that you have the possibility to install a protection device at the connection point. That means you need current transformer there, you need a place to install it, and you also need a DC voltage to supply it, and also you need the communication to the right end. So that was the application on mixed feeder, cable and overhead lines. So we are through our 3 topics. I can make a short conclusion. So for distance protection on short lines or mixed lines and in system with earth fault compensation, we saw that we have to think about a few additional things so that the application runs smoothly, and I have discussed them here a bit more in detail. Thank you for listening.
Dear audience, if you're interested in more detailed information and practical training, please visit our training platform at Siemens Power Academy. I am confident you will find the right resources and training there. A link to the recording and the slides will be sent to all participants. Thank you for your active participation. I look forward to meeting you soon. Stay safe and take care. Goodbye.